Okay, so today I'm going to go over the final exam review. Unfortunately, I do not have a copy of it. I printed out. I actually don't have a printer, so what I'm going to do instead is just work it out on my notebook here, and I'll write out the questions as I go through. So the first one is a Newman projection question. Let me just get situated so I can make sure I can see that I'm in the camera. Is a Newman projection question, and so it has a structure drawn like this. OH. And the question is, which of the following is an appropriate representation of the molecule in the box when looking down the C2-C3 bond? So what I would do on this question is actually, even though it's multiple choice, I would not look at the answer choices quite yet. I would just draw the Newman projection. So that if I'm looking at it from the C2-C3 bond, that's through here. So this wedge is coming out towards me, so it must be on the right, and then there's an implied hydrogen going in. And then this CH3 group is pointing up, and then the back carbon, I can do that in a different color. There's a CH3 right here, and a hydrogen that's implied going into the plane of the page. And then this ethyl group pointing down. The CH3 kind of has gotten lost, so I'll make it more prominent. So first I draw my Newman projection, and then I compare it to the different answer choices. So answer choice A actually looks like it has this as part of the front carbon, as if you're actually looking through the C3 to C2 bond. So because answer choice A has this on the front carbon right here, that's not correct, because that should be on the back carbon, because that's on C3. So this is an improper visualization of the molecule. Or that's actually answer choice 1. Answer choice 2, nothing is immediately obvious to me about answer choice 2. Oh, also, I guess I should say, I haven't seen these questions before. I mean, I've seen them in that, I put this worksheet together, but I didn't try to come up with the answers or know which one was the right answer. I took them from other places so that you could see a genuine process of me working through them. So this is literally what I would do if I was taking this same exam. So 2, what I'm going to do on this one is I'm going to look to see if all the right things are attached. So the alcohol, the hydrogen, and the CH3 are on the front. On the back, we have a CH3, the carbon-carbon double bond, and the hydrogen. So this one looks like it could be. So I'm just going to write could be and come back to it. Question 3 looks like it has a CH3, hydrogen, and OH on the front. And on the back, it has the CH3 hydrogen and then the carbon-carbon double bond. So I'll put could be for 3 as well. And then I'll come back and check, with the rotation if it's accurate. 4, on the front, it has a CH3, the OH, and the hydrogen. And on the back, it also has a CH3, the H, and the carbon-carbon double bond. So 4 could be as well. I'm just doing an immediate walkthrough. It's is this possible at all for this to even be it? And then 5 as well. Looks like it could be. So actually 5 looks exactly the same to me as the one I have drawn here. It has the carbon-carbon double bond on the bottom, an alcohol, a hydrogen, a CH3, a hydrogen, and then the CH3 on the top. So I think 5 is definitely at least one right answer. But if you look at the answer choices, there's multiple right answers. It looks like, there's 1, 2, there's 3 answer choices that have 5 in it. So you can, there's A, B, C, D, and E. E is none, so we know that's not right because 5 is accurate. D is 5, C is 3, and 4, so we know that's not right because 5 is definitely correct. 2 and 5, and A is 1, 2, and 5. So I can eliminate it down to just A, B, and D based only on that. So now we have to look at the only other possibilities it looks like is 1 and 2, but I'll go through all of them for you. 3 is not on these other answer choices, and neither is 4. But we know actually already that one's not right. We already decided that it was through the C3C2 bond. So actually with that, I can eliminate A as well. So just looking for the one that was exactly like I drew and knowing that the wrong things were connected to the wrong atoms, we can eliminate 3 answer choices. So we're down to it only being 5 or it being 5 and 2. So I actually don't even have to look at the other options, but I'm going to anyway just to see what's right or wrong with them. So first, let's start with 2. It looks to me like what's happening with 2, what I like to do is I like to check sort of the order of rotation. So on the front atom, it looks like the alcohol has been moved. Oh, it's moved over. Oh, the whole atom looks like it's rotated. Okay, the alcohol has been moved over here, so I'll redraw it. They flipped our Y upside down here. So the alcohol used to be here, and now it's ended up here. The CH3 used to be up top, and now it's straight down, and the hydrogen is over here. So it just looks like they rotated that, like instead of 60 degrees like they normally do, they rotated about, I think it's 90 degrees is what it looks like to me. Something like that, or maybe like 100. So they didn't do the full 60-degree rotation. They kind of made it look a little bit weird. But it is still correct. And then the back atom, it looks like they sort of did the same thing where they have the CH3 going straight up, and then they have the hydrogen, or they have the carbon-carbon double bond going straight up, and then the CH3 over here, and then the hydrogen over here. So it looks like basically what they did is they took this whole molecule and they rotated it 180 degrees. So if you flipped this upside down, this is exactly what answer choice 2 looks like. So it's the same molecule, and it's actually even the same conformation. It's just they rotated the whole molecule. So instead of us looking at it like this, what this question has going on is like they basically did, this becomes, no, yeah, that's right. I think they just did it like this, or this is a dash and this is a dash, I think. So they basically just like literally flipped the molecule over like that to give us it should be dash, to give us 2. So just with that, we know that B is right. I'm going to talk about why all the other ones are wrong anyway. 3, it looks like is, I'm going to look at the front carbon first. It should have alcohol and then CH3 and hydrogen. So the front carbon looks right. Oh, but the alcohol and the CH3 are both wedges, which means they need to be on the same side of the molecule. So in carbon 3, they're not on the same side of the molecule. So basically carbon 3 is a diastereomer. Carbon 3 represents this molecule instead of that molecule. So it's not the same molecule, or structure 3. I might have said carbon 3. And then for structure 4, it looks like they kind of did the same thing, but with a front carbon. So the structure 4 represents this one. So this is good practice for you if you're, this is structure 4. And this is what structure 2 represents. This is good practice for you if you're wanting to improve, your stereochemistry or your representations and Newman projections and stuff. What I was able to do, I was able to find the 2 that were right, but I was also able to convert what the wrong ones were representing, and that could be something that's valuable to you. So for number 1, I'm going to make it my answer key as we go through because I still have to grade this. So for number 1, the answer is 2 and 5, so that's answer B. Okay. Question 2, use the following molecules for questions 2 through 4. I'll just go ahead and flip over. So these are the Fischer projections. CH2OH, HHOH, H, and CH3. HOH, CH3, CH3, HOH, CH3, OH, H, CH3, OH, H, and over here, I'll make this one very small. CH3, OH, H, OH, CH3, and H. Okay, so which of the following is an appropriate representation of the molecule? Oh, nope. Use the following molecules for question 2 through 4. Assign R and S configuration to each of these. Be sure to include all chiral centers. Okay, so this is 1, 2, 3, 4. So you can do this one of several ways. You can either just go through and assign every single one, or you don't have to. You can kind of look for patterns. But first we'll start by assigning. This is actually not a chiral center because 2 hydrogens are the same. So there's only 1 chiral center for this one. Alcohol is going to be the highest priority, and then these are both carbons. So if they're both carbons, then you have to look at and see what's next. So this carbon down here is attached to another carbon and 2 hydrogens, and this carbon up here is attached to an alcohol and an oxygen, and 2 hydrogens. So this would get higher priority. So 1, 2, and 3. So this is going to the left, so that's S, but the hydrogen is pointing towards us. That's the lowest priority. It should be pointing away, so we actually have to flip it because we're through the looking glass. Okay, so carbon 1, 2. 2 R on this one. Let's see. And then for 2, we have 1, 2, 3. So this is S, and the hydrogen's already pointing away from us, so that's right. And then on this one, we have 1, 2, 3. That's R, but the hydrogen is actually pointing towards us, so we're in the looking glass. So this is actually 2S, 3S for the configuration on that. This is 1, 2, 3. So this is S, but the hydrogen's pointing towards us, so it's actually R. And then 1, 2, 3. So this is R as well, and the hydrogen's already pointing away. So both of these are R. But one thing you could have possibly noticed is that the bottom of these two, it's kind of hard to see now that I've drawn over them, but you can look back at the actual paper assignment with it if you want to, the file. But for 2 and 3, the bottom carbons, they both have CH3 on the right, but this one is hydrogen-oxygen, and this one is oxygen-hydrogen. So you can just see that these two have swapped. So I'll go ahead and draw these back out for you a little bit neater. Since you've already assigned the priority in order to this one, you can make your life a little bit easier by just comparing these two. So the OH on the top one is in the same place, but the CH and the hydrogen have swapped, which must mean that whatever the chiral center is on here, this one's the opposite because we interchanged 2 groups. And we learned that if you interchange 2 groups, then it must be the opposite. And then the same thing down here. The CH3 is in the same place, but the alcohol and the hydrogen traded places. So this must be the opposite. And that holds up because we get 2S, 3S, or 2S, 3S, and 2R, 3R. And then this last one, 1, 2, 3. You could actually do this again with this last one. The alcohol is over on this side. The CH3 is in the same place. The hydrogen and alcohol have switched places. So I'm going to guess that this one's actually S, but I'll go ahead and assign it. 1, 2, 3. R, but the hydrogen's pointing towards us, so it's actually S. And I'm going to redraw this down here so it's easier to see. And then 1, 2, 3. And again, this has is any group of this lined up with anything? The alcohol is in the same place as this one down here, but the hydrogen and the CH3 have traded places, so I'm going to guess this one is R. 1, If that's too confusing for you, just do it the way that you're used to. That's S, but the hydrogen's pointing towards us, so that's R. Okay, and when I see, well, first I'll finish saying, if that's too confusing for you, you can just do what I did and assign the configurations to every single one of them. That's totally valid. You are totally welcome to do that. It's up to you. I will usually kind of check myself. Like I'll double check that I just swapped two groups to interchange. Like if this is supposedly 2R3S, oh no, it's the opposite. If this is 2S3R, then I'm going to compare this R to that R. And does it look the same except rotated? Yeah, the CH3 here is rotated over, the alcohol's moved down, and the hydrogen's moved up. So that's rotated, not swapped, so that is the same. And then I'll check myself again over here. The alcohol moves this way, hydrogen moves up, CH3 moves over there. So yeah, the top carbon is the same. So you can check yourself after you've assigned the configuration to make sure that you did it right if you're not sure. Okay, so the next question is, which of the following is a pair of diastereomers? Well, just from looking at this, conveniently, I know that SS and RR will be enantiomers, right? Because they're mirror images of each other. If you know that just from the letters, that's fine. Sometimes it actually helps to line things up. So I'm going to rotate molecule 3 to have the CH3 line up with that CH3OH. So I move the CH3 here, the OH over, and the hydrogen up. And then I'll do the same thing on the bottom. I'm going to move, I'll move the CH3 over here. I'll move the OH down and the hydrogen over. And you can see the CH3s would reflect each other in the mirror image. The hydrogen and the OH are on the top, and the OH and the H are on the other side. So you can see the plane of symmetry easily there, and so it's easier to kind of reflect. So either way of these that makes sense to you, these are enantiomers. So if these are enantiomers, and then we have an SNR configuration, then hopefully you recognize that these would be diastereomers. So my answer to this question would be there's more than one pair of diastereomers because 2 and 4 are diastereomers, and so is 3 and 4. Okay, but 1 doesn't have the same number of chiral centers, so actually 1 I think would probably, it looks like it is a constitutional isomer because it has 2 alcohol groups. Yeah, it looks like a constitutional isomer. 1, 2, 3, 4 carbons. So the relationship of 1 with all of these other ones, 1 to all of these is constitutional. But there's 2 different sets of diastereomers. Okay, and then the last one is which one of the following are achiral? Oh, I didn't put a C in that. Achiral is what I wrote. Okay, so when I see something that all 3 of the same groups attached to the top and the bottom like this, for all of these centers, you have 3 groups, and one of them is an OH, a CH3, and a hydrogen. And then the same thing on the bottom, OH, CH3, and a hydrogen. That's a red flag to me that an achiral meso compound could be there. And this is a meso compound specifically is a compound that has 2 or more chiral centers. It really has to be an even number, I think. But the mirror image is imposable. It is superimposable. So it's not a chiral molecule, even though it has, it's not chiral despite its chiral centers. So the thing about that is it's a mirror image across itself. So if I see 3 things that are the same attached like this, OH, CH3, and H, same on top and bottom, there's 2 chiral centers, that's a red flag for me, or like oh, there could be a meso compound here. And usually the S and R configuration, the way it reflects across for these to be mirror images of each other, that one is the one you have to look out for it being achiral. So immediately I'm looking for that. But also these are already lined up in a way that kind of makes it easier for you to see, right? Because these CH3s are lined up, so the rest of it's not reflecting across the mirror image. So 2 can't be it. 1 can't be it because there's only one chiral center. 3, again, already has these alcohol lined up, but the other 2 aren't lining up, so that's not right. So then let's get things lined up here on molecule 4. So I'm just going to pick the alcohols. I'm going to line the alcohols up. So I'll rotate this bottom one to where the OH is here. The hydrogen will be here, and the CH3 will be pointing down. There's a line through the middle right there. You can see that it does reflect across. So just by rotating one, you can see pretty quickly that this is a meso compound. So if the same things are attached, there's 2 chiral centers, and you have an SR configuration, that one's going to be your meso compound, but you can always rotate to check yourself. So let me go fill in these answer choices because I've done a lot of them. Okay, so let's see. We said 1 was B, 1B, and then 2 I just did was the chiral centers for 1, 2, 3, and 4. So 3 was RS, or 4 was RS. 3 was it RR? 3 was RR. 4 was SS, and 1 was just plain old R. Okay, 3 asked, 3 was, which of the following is a pair of diastereomers? And the answer was E. There's more than one of these is a pair of diastereomers. And then, which of the following are achiral? For 4, the answer was D is achiral because it was the meso compound. So even though it had 2 chiral centers, it was achiral. Okay, so question 5 is asking which one of these is trans 1,3-dibromocyclohexane. So I'm not even going to look at the answer choices yet. I'm just going to draw it out. So 1,3-dibromo, so bromo, 1, 2, 3. And they're trans, so one's a wedge and one's a dash. So I like to draw it in the ring first and then convert it to the chair conformation. So if this bromine is pointing up, and then this one is pointing down, that must mean it is, let's see, now I've lost track. This one pointing down would be axial, so this one pointing down would be equatorial. This would be axial, and the hydrogen on the wedge here is equatorial, and the hydrogen here would be axial. Okay, so this bromine is equatorial. So we need 1 axial, 1 equatorial, and we need 1 pointing up, 1 pointing down, which naturally they should be if they're in axial and equatorial like this. So now I'm going to go look at my answer choices. And the answer choice 1, I immediately see they kind of have their chair drawn slightly differently than me, but it looks like they have 1, 2, 3, both up and equatorial. So this actually represents, I would say, cis dibromo, where they're both pointing up and they're both equatorial. 3 looks like the exact same structure I drew. Oh, except I do have my equatorial pointing the wrong way. Sorry. That looks better than mine, so I'm going to fix it. The equatorial goes down this way. Okay. So 2 actually looks like a good option. And then 3 looks like 3 also looks like a good option. One's axial and one's equatorial. So 3, it does move around a little bit. They have the one that's pointing down. Let's see. Okay, I actually think this might be an enantiomer of my original one because they have 3 pointing down and this one pointing up. So if I converted, sorry, those are bromine. So if I converted that back, it actually, this bromine is pointing up as the wedge and this one is pointing as a dash. And I think that is the mirror image of what I've drawn here. Now, I did not specify our S configuration in trans 1,3-dibromocyclohexane. So technically, both of these enantiomers are trans 1,3-dibromocyclohexane, but that kind of tripped me up for a second initially. But they both are correct. It's just that they're enantiomers of each other. It just so happens. I was like, wait, that's not the same molecule. So I think 2 and 3 both fit the bill of trans 1,3-dibromocyclohexane. And that's why we need RNS configuration so that you can tell which one of these is which enantiomer, right? I think it would be different enantiomers. I'll just do a quick check. See, this is what you don't see when you get my nice polished videos. This would be R configuration, and the hydrogen's already pointing back, so that's fine. And then 1, 2, 3. This is S, and the hydrogen's pointing towards us. There's an implied hydrogen, so this is actually R. So this one's RR, and then let's see, 1, 2, 3. So this one's S, and the hydrogen's already pointing away from us. Yeah, so this is 1, 2, 3. And that's R, but the hydrogen is pointing towards us, so that's S. So yes, it is 2 different enantiomers. Okay, that was kind of satisfying. But they're still both trans 1,3-dibromocyclohexane, but you can kind of push your knowledge and understanding of the material further by just on this one question asking yourself more. So I would say for question 5, you could have eliminated A and B because they both contain 1, and we immediately eliminated that one was cis 1,3-dibromocyclohexane. So then you had already narrowed it down to just C, D, or E. And C is just 2, D is 2 and 3, and E is just 3. So we found that both 2 and 3 represent different enantiomers, but they're both trans 1,3-dibromocyclohexane. So for question 5, my answer is D. Okay, now let's go to question 6. I'm going slowly through all these. That's kind of what happens when I talk out loud through my whole process. And also it's part of a study technique is that I want you to see all of the things that you can do with just 1 or 2 questions rather than only answering the question at hand. There's a lot more that you can test yourself on here than just what I asked you in these questions. Okay, so what's the relationship between these 2 molecules? This is a Fischer projection. There's a hydrogen, hydrogen, bromine. Bromine, that bromine's way off to the side, and a chlorine. And this one is chlorine, chlorine, bromine, hydrogen, bromine, hydrogen. Okay, well, right off the bat, I noticed that I drew my hydrogens and chlorines look shockingly similar. I noticed that I drew 2 bromines over here and 2 bromines over here, but I only drew 1 chlorine over here and 2 chlorines over here. So just based on that, I don't think these are isomers because isomers have to have the same number of carbons, hydrogens, bromines, chlorines, and whatever else is present. And the one on the left has, they both have 2 carbons. So that's the same on both sides, 2 carbons. And they have, this one has 1, 2, 3 hydrogens, but the one on the right only has 2 hydrogens. And then this one has 2 bromines, so does the one on the right. And then this one has 1 chlorine. I wrote bromine instead of 2. And this one has 2. So basically they replace a bromine with a hydrogen. So these are not isomers. So you could have gotten really focused in on like, oh, diastereomers, this, that, and the other. But if you didn't notice that there's not 2 chlorines on there, then you straight up, it's like, well, okay, these aren't isomers. You can test yourself further if you want by going through and like making the diastereomers of these, like drawing the enantiomers, checking them with RNS, but you don't have to do that. Okay, so question 6, this answer was A, not isomers. Okay, question 7. 1 and 2 are, what's the relationship between 1 and 2? I got a lot of questions to go back over this part of the class. This is like chapter 5 type stuff where you look at the relationship between two molecules. This one has an OH pointing up axial, a CH3 pointing up axial, and a bromine pointing down. And this one has an OH. Oh, this isn't focused. There we go. An OH, a CH3 pointing up, and this bromine pointing down. Okay, so the first thing I see is this looks exactly the same. Carbons 2 and 4 look exactly the same. The CH3 pointing up axial is the same on carbon 2, and the bromine pointing axially down is the same on carbon 4. There's only one chiral center, one place that's different, and that's carbon 1. And so straight off the bat, I'm thinking there's only one place that's different, but there's multiple chiral centers, then that has to be a diastereomer. So remember, if you're looking at isomers, you have constitutional isomers, which are, that looks terrible. I'll fix it. I love this rocket book. It's amazing. Okay. Isomers, you have constitutional, which is like if it has the same number but they're arranged differently. A really common example is these two things. And then you have stereoisomers. And stereoisomers are broken into enantiomers, which are non-superimposable mirror images, and diastereomers, which are everything else. So these don't look like mirror images to me, so these are not enantiomers. But they're also not constitutional isomers. They have the same number of everything attached. They're definitely isomers, so the only thing left is diastereomers. There are stereoisomers that are not enantiomers because they have the same molecular formula, so they can't be constitutional. Everything, they're isomers, period, because everything that's on them is the same. So if they're not mirror images, then the only thing left is diastereomers. If it's hard for you to see in this, in the chair conformation also, you can draw it out. So I usually just make up a dash because it feels like pointing up is pointing towards me. So that's what I do. So carbon 1 has an OH that's a dash. Carbon 2 has a CH3 that's a dash. And carbon 4 has a bromine that's a wedge. But on this one, this OH is pointing down. It's in the equatorial down position. So that's a dash. And then this CH3 would be the same and the bromine would be the same. So you can see it really well here if you draw it out like that. And then obviously you can also do your axial, equatorial, axial, equatorial, axial, equatorial, where you fill this in and then you can convert back and forth, if that helps you. Go from boat to chair and vice versa. So this one's axial, so I'm just going to arbitrarily assign that axial there is a wedge, and then this next one is equatorial. It's not pointing straight up or down, it's pointing up at an angle, so that's equatorial. So that must also be a wedge. And then we go to carbon 4, and it's pointing down axially. It's not an equatorial, so that must be a dash. This would be the axial position. So that's kind of how, those are some ways that I would process through that. But when you have it drawn out like this, it's much easier, in my opinion, to see that these are the same, and only one is swapped out. So that one must be a diastereomer. Okay, so question 7, the answer is D, diastereomers. Okay, and now let's do 8. Select the structure of the product formed in the following reaction. So this is an alkane with Br2 and light. H nu is light. So if I just saw this right here, and I wasn't sure what kind of reaction this would be, I would go through my list. This is not acid-base because there's not a clear acid or base here. This is not a substitution or elimination because there's not a good leaving group, right? Not a good leaving group, not a good nucleophile, can't be substitution or elimination. The next thing we learned were addition reactions, but there's no double bond to add to. Br2 is a good candidate for an addition reaction, but there's no double bond to add to. So that's chapters 3. 4 and 5 were about stereochemistry. This is 6 and 7, chapter 8. So the only thing left is chapter 10, which is radical reactions. So this is probably a radical reaction. So my first thought is that there will be an initiation step, and then a propagation step where one of these radicals will come and abstract a hydrogen. And in bromination, it will always abstract the most substituted, the most stable radical. So it'll go right here. And then this other one will come and combine, and you'll get your radical addition of bromine. So the answer choice that looks correct to me is answer choice 2. This is in line with 2. So I like to go back and look at my answers and see what they've got going on and why the other ones aren't right, just to convince myself of why I chose the right answer. And so A has, it does look like it did a radical reaction, but it's not in the most stable position. So that's why A is wrong. And then the same thing with C. So the structures for A and C would be viable options if this was a radical reaction. But because this isn't a radical reaction, the major product is going to be answer choice B. 4 is just totally wrong because it gets rid of a CH3, and then 5, again, has a bromine there somewhere where it would be if it was a radical reaction, or with chlorine, not bromine, but because it's bromine, it's more selective. Okay. So that's question 8. Let's go into 9. Question 9 is, which of the following... Oh, geez. What was that? Sorry. Something just hit my door. Okay, don't worry. My husband just freaking terrified me. He opened a door and it slammed the door right next to me shut. So he didn't do it on purpose. He's not the kind of mean guy who plays pranks, but it did scare me sufficiently. Okay, so we've got Br2 and H nu for the first step here. And the second step is MEONA, MEOH, and heat. Okay. So what will be the major product of the following reaction in this reaction sequence? So the first thing is bromination. And so again, we just talked about how if there's not a good leaving group, no double bond, then bromine, especially if it's with heat or light, is going to do a radical reaction. So same thought process as the last one. It makes 2 radicals and it will abstract a hydrogen. Let's make sure 1, 2, 3. There's a hydrogen here or here. It's symmetrical, so I think it will take either one of those. Is there 1, 2, 3, 4? I was worried I had drawn 5 bonds to carbon, but no, that's correct. So this will come and bond with one of them. Really, that radical initiates it. And you're left with a radical formation right here on the most stable position on the bromine. If it was chlorine, there'd be all kinds of reactions. And then the other one forms right there. Make sure you do a single barbed arrow. I'll be grading for that on your homework. And then you get your bromine. So that's the first step, is a bromination of the alkane to make the second step possible. So the second step is MEONA, MEOH, and heat. Sometimes heat is just drawn with the triangle here. Okay, so if I see this, I know it's not an acid-base reaction because there's not an obvious acid-base. So then the next type of reaction we learned was substitution, elimination reactions. And there's a good leaving group, and there seems to be a good nucleophile. So I think this is a substitution elimination. So then the question a lot of people asked me was, they wanted practice telling if this was a substitution or elimination. So I look at the nucleophile, and this nucleophile, MEONA, is actually MEO minus and Na plus, right? They're just hanging out close together. So MEO minus is a strong nucleophile. So if it's a strong nucleophile, it favors 2. If it's a weak, it goes towards 1. And then if it's heat, it favors E2. If there is no heat, and also because it's tertiary, it favors E2. If it was secondary and there is no heat, I could see it going for SN2, but I'm going to say this favors E2 because of all those things. So, and the bromine is right here, so we've got to identify our beta carbons. There's 3 beta carbons. Here, here, and here. These 2 are basically the same, so there's only 2. So I'm going to go ahead and draw out if I got a Hofmann and Zaitsev product. So if it was here, it would fill in right there. And if it's here, bleeding your bleeds. So this one seems to be the more substituted to me, so that seems to be the more stable. This one over here is only tri-substituted, so this one would be Zaitsev, and this would be Hofmann. We have a narrow nucleophile, so Zaitsev is favored, but the last thing I want to think about and check for is stereochemistry. Except they didn't give us any stereochemistry, so we can't tell if there's a hydrogen that's anti-periplanar, so we're going to just have to assume that there is one there because they didn't really tell us. So I think the major product in that reaction sequence would be answer choice C that looks like that, because it's a narrow nucleophile, so it favors Zaitsev. So I'll go through. This is C. So 1 seems to be wrong to me because they didn't do the elimination. They just did step 1. 2 is the right answer. Oh, wait, no. This is 3. That's the right answer. 2 would be the right answer if they had a bulkier nucleophile to favor Hofmann. 3 is right. 4, I think, would only have taken place if you had chosen the wrong place for the radical to go, the less stable place for the radical to go, because it takes from a beta hydrogen that's too far away from the radical or from the halogen that we added on that one. And then the last one just looks like they did the wrong radical reaction completely, and it says something plus an enantiomer, but it doesn't even have the stereochemistry. So I take issue with answer choice 5. It's wrong on so many levels. Very wrong. Okay, so all that to say, I think the answer for question 9 is answer choice C. Okay. Let's go to 10. Oh, a lot of you asked me about 10. So we started with this molecule, and I basically just wanted you to practice a bunch of different addition reactions because a lot of students also asked me about that. So question 10 is if we reacted this with Br2 and heat. And a lot of students asked me, then they answered it themselves. So I'm going to go through the same thing that I asked them. They said, I can't tell if this is a substitution elimination, radical, or addition reaction. And I agree that this would be a good candidate for addition normally because we've seen Br2 add to double bonds at times. So I would ask them, can it be a substitution or elimination? You need a good leaving group and a good nucleophile. There's not a good leaving group or a good nucleophile there, and you can't do substitution or elimination on sp hybrid, so I'm going to say no. The next question is, could it be a radical reaction? Well, we have a radical, and we have a radical initiator and an alkane for it to add to, so I think that's a good possibility. And then the last question is, could it be an addition reaction? Well, typically with addition reactions, we do these at colder temps if bromine is involved because it's a radical initiator. So if there's heat or light explicitly present, like there is here in this scenario, I'm going to favor, although an addition reaction is possible, I'm going to favor the radical reaction over that. And this is a highly controlled reaction because bromine is much more stable than like if you were to have chlorine. And so then the next question I got asked, oh, that's a cyclohexane. The next question I got asked a lot was, then where would the bromine go? And a lot of students had forgotten that we talked specifically about where a radical forms if a double bond is present and where it doesn't form if a double bond is present. And that is, hopefully you remember the names of these. There's the allylic position and the vinylic position. So a vinylic position is when a radical abstracts a hydrogen and leaves a radical behind right on a double bond. This is bad news. Okay, this doesn't really happen. This is not favored. However, the allylic position, we talked about how it can partake in resonance and spread the effect of the radical into two different locations. So this is very stable. So when I think of radicals in general, they follow carbocations. And carbocations also really don't like being at the vinylic position, but they like being at the allylic position and the benzylic position. So that's my order of radical and carbocation stability. So then that's where this one's going to go. It'll go to the allylic position. So I'm going to draw this out. Actually, it's happening though. So one bromine will come and take a hydrogen from there, and that hydrogen will leave with its electron, and you'll get a allylic radical. And then the other bromine will bond with that in a termination step, and you get your bromine added right here. So you notice I initially had the radical here at the allylic position or here. Because there's symmetry, either one of these would give the same product. So either one of those is okay. So this is my prediction of the product. Now, 11 is very similar. It has a radical initiator, Cl2 with light. So it has a radical with the radical initiator of light, and so it'll make your two chlorines, but chlorine is a lot less controlled of a reaction. So it will take a hydrogen from pretty much anywhere it can. I don't think it will take from the vinylic position though, because it's crazy, but it's not that, it'll do whatever it wants, but it can't really do something that unstable. So actually the radical will form at either of these two positions, and I'm not going to go through the whole mechanism, but essentially that's where the chlorine will end up adding. It goes through the same mechanism as the one above. And again, because of the symmetry, there's only two places. These are the same here and here, and there and there. So I think these would be the products. That looks like I drew a radical there, but I didn't mean to. These would be the products for question 11. So I should probably draw this on my answer key over here. So 10 is an allylic bromine, and 11 is an allylic chlorine and a chlorine 1 away from that position. Okay. Now question 12 is predict the products if you reacted the molecule. 12 is if it underwent oxymercuration, demercuration. So one way that I kind of tell students to check themselves is oxymercuration, demercuration is very similar, but not exactly the same as the carbocation reaction. So it would have the positive charge. At this step, an acid catalyzed would undergo rearrangement. But if in this case there's not a possibility for rearrangement, and therefore the oxygen would attack right here and it would eventually get deprotonated. Now this is not the oxymercuration demercuration. This is the acid catalyzed hydration. But acid catalyzed hydration and oxymercuration and demercuration both go by Markov-Nikov. The biggest difference is that oxymercuration demercuration doesn't undergo rearrangement. And students usually understand this mechanism a lot better than the other one. So if you're having trouble and you get asked an oxymercuration demercuration question, check yourself by looking at the carbocation acid catalyzed mechanism. But this is not the correct mechanism. What actually happens is this would attack and one of these bonds would break, and you end up with, basically a carbocation, but there's a positive charge here, HGOAC here, and then the HGOAC will lend some of its electron density, becoming partially positive itself, and leaving a partial positive here, and this is our bridged ion. But the strong partial positive is right here, and that is where your nucleophile will come in and attack. And for oxymercuration, demercuration, that nucleophile is water. So the water will come in and attack right there. And your initial step would be the addition of HGOAC here and water over here, and that would add anti. But the next step that reduces the HGOAC to hydrogen actually goes through this part. Like this is OH2 plus, and it gets deprotonated to OH minus H plus. Okay, so then you go through the reduction step, which is also, I didn't draw the bond there. I'm having all kinds of struggles. I'm trying to talk and write at the same time, and my brain's not letting me do it. So you have HGOAC and your water, which has been deprotonated down at the bottom. And then it'll undergo, originally this adds like anti, I mean, this isn't a chiral center, so it doesn't really matter, but when it goes through the reduction step to get rid of that HGOC and replace it with hydrogen, it scrambles the stereochemistry. So you would get this, you could do the wedge or the dash plus the enantiomer of that one. And you don't have to draw this implied hydrogen because it's implied. So you can just do OH with the wedge and the dash like that. So that's the answer that I got to question 12 is it would be OH plus enantiomer. Okay, and then question 13. Predict the product if the molecule underwent hydrogenation oxidation. So that one is anti-Markovnikov. So if we have this, and notice we, in the last one, figured out what the Markovnikov product looks like. So if you are just trying to go quickly, anti-Markovnikov product looks like this, and that's your answer. But that's not always the best way to go. I like to draw the, you're not responsible for this though, I like to draw the box out, the BH2 with the hydrogen over here, and then it's making BH2 and hydrogen, and then BH2 gets replaced with OH, and that's how you get your answer. So that's the answer. It would add SYN, the hydrogen, and the OH, but that's not a chiral center up there, so it does not matter. So question 13, the answer is OH, like that. Okay. Predict the product if the molecule underwent acid catalyzed hydration. Oh, I already did that. Nice. I didn't realize I had that question on there. There's no rearrangement, so the acid catalyzed hydration reaction is actually the same as the oxymercuration demercuration. And it just so happened that I'd already worked that out to check myself on the oxymercuration demercuration question. So I did myself a favor there. Predict the product if you reacted the molecule with Br2 and CCl4. So again, all these were clearly addition. You've memorized these names, so hopefully remember all these are adding water across a double bond. But Br2, that could be addition, or it could be addition of Br2. It could be halohydrin. So this is 15. Br2 with H2O could be halohydrin. Br2 with methanol or some other kind of alcohol can make an ether. Br2 in CCl4 does addition reaction, just a plain bromine on each side. And Br2, in the presence of heat or light, will do a radical reaction. So when you see Br2, you really need to think about what kind of reaction this might be. We've already done the radical reaction, and it looks like it gives us that the solvent is CCl4. So that tells me that this is going to add bromine across the double bond. And I'll go ahead and draw out the mechanism for you. it adds Markovnikov fashion. So the bromine would add here, and there was a partial positive, but plus the Br minus over here. But this donates its extra electron density, making a bridged partial positive there, partial positive there. We have our bridged ion formation, and then this comes and this bond breaks, and that's how you get a bromine here. And then this will, these have, technically, I'll redraw this for you. So technically, this will have added one bromine this way. They add anti and one bromine a dash, but this right here is not a chiral center because there's two hydrogens. So you don't really need to draw your dash there, but you absolutely need to draw your dash here because this is a chiral center. And if you have it drawn as a flat line with one dash, that is representing that this is a plane with one thing coming straight at you, and that's not correct. So the right answer is actually this, which is kind of weird. But technically, I mean, it does add where the bromine initially is a wedge and that's a dash, but this can just rotate all around. It's not a chiral center, so you don't need to draw the 3D structure. So the answer for 13 is, nope, that was 15, is bromine added across the double bond plus the enantiomer, because it can attack from either side. Okay. What reagents would you need to generate a halohydrin? Well, I already went through all the different things that you need to generate different stuff with Br2, so I already answered that question for myself, kind of. So Br2, if you have a double bond like this, if you have Br2 in H2O, it will do a very similar reaction where initially it adds the bromine with a partial positive here and a partial positive here, but then the water attacks and breaks this bond, and you get your bromine up here and your water. That's actually OH2 plus, and then it gets deprotonated. You can also draw it this way and write racemic mixture if you don't want to draw out the wedge and the dash like I made you before, but you definitely can't do one dash and one straight line. You can either do both or neither. It generates a racemic mixture because this can attack from the top or the bottom. So for right here, it generates a racemic mixture. Got to do your deprotonation step, and that's what you need to get a halohydrin. So this is a halohydrin, so you just need, for 16, you just need Br2 and H2O with that alkene. I'm assuming you would just use the same alkene. Okay, and now the last question, 17, is the last one with that alkene, is how would you convert this molecule to this molecule? And I can tell you, when I look at this, I say this literally doesn't do anything. There's no functionality to it. So that's basically why we learned radical reaction. So I'm thinking at first, I would love to do a radical reaction to get this to have some kind of functionality. And we've already done a reaction where we had this and we did a radical reaction and we got bromine, actually. I think we did this exact one earlier. Maybe not. It was an allylic one. Yes, right here, question 8. This is the exact same question as question 8. So it's kind of a hint that hopefully you've seen before. And then if you have this, which is a good leaving group, and you want to turn it into a double bond, what kind of reaction can you do? An elimination reaction. Hopefully you remember. And to get the less substituted product over the more substituted product, you would need to use a big, bulky nucleophile like tert butoxide. And it's possible, I actually probably wouldn't use tert butoxide. I'd use tert butyl alcohol because this is, oh no, it's tertiary, so it can undergo E2 or E1 or E2. So you could use tert butoxide. with heat to undergo an elimination reaction, or you could do an SN1 where you kind of have like a weak tert-butyl alcohol and heat. Either one of those would be fine. But if you combine this with a good bulky nucleophile and heat over an elimination reaction, and you'll get your Hoffman product. So that's my proposed way of working through it. Is I sort of, some people work backwards, like they say, okay, I've got a double bond. How do you go from a double bond to the thing before it? For me, it's easier to look at the starting material and the ending material and see what changed and figure out how I can get from point A to point B. So it kind of just depends on what's easiest for you, but I would do a two-step reaction, one with Br2 and HNu, and then an elimination. And for the elimination, whatever your group chose to do is fine, but I would probably go for this. And I can look at your group's work and figure out, what you were thinking and if it works. So that's what I would do for 17. Okay, let's go to question 18. How many chiral centers are there in this drug? Oh, my webcam seems to be getting kind of choppy, so I'm actually gonna stop this, and I'm a little bit less than halfway through. I'll stop this, upload it, and then do part 2.